Hi, next we are going to do binary to BCD conversion, in which we are going to take an 8-bit binary input from slide switch and display that BCD output on LEDs. Let's quickly start that project. So name it as binary to BCD. This project will be helpful. We already created BCD to 7 segment display, but our 4x4 multiplier is of binary output that we have to convert it to BCD format before displaying it to 7 segment display. That's why we are doing this project. So create a new source. Finish. Okay, what are all the inputs that are required includes, first we need clock input and binary in, with binary in will be of 8 bits, 7 down to 0. Then we have 3 outputs like BCD 0, BCD 1, BCD 2. So each of them of 4 bits. So we will assign each BCD output to LEDs. That is 3 down to 0 here. So LED, first 4 LED will be assigned to BCD 0, 1 and 2 like that. BCD 0, BCD 1, BCD 2. Okay. Then we assign some signals. One of the signal is we give that BCD into something called being before processing. Again now 7 down to 0. Then we will be having a signal with the name of ones, tens and hundreds. So I mistakenly written as in, so it is a signal. std underscore logic underscore vector. This is of 3 down to 0. Then we have some signal that is we will check some conditions like initially we assign the input to binary. We keep all the inputs to initial state, that is the first logic. Then after that we will do the binary to BCD conversion. Then after doing that, once we got ones, tens and hundreds, then we will assign those outputs to BCD 0, BCD 1 and BCD 2. So we have something like 3 case statements. So 3 states. We have assigned something called state with std underscore logic underscore vector of something like we can make it as 1 down to 0. So we will have some 3 states that we do one by one. Let's open a process. I'll show you that flow diagram. This is the flow. First it takes the binary input, and that binary input will be assigned to binary in. Then all tens, hundreds, thousands will be, ones, tens, 100 will be assigned with zeros. So then after that it will do some logic operations in state. This is the state 0, 0, 0. After initializing all values, it goes to state 0, 0, 1 or 0, 1. In that one, it will check whether the binary input is greater than or equal to 100. Let's say if it is 999, it will check if it is greater than that. Yes, it is greater than that. So it will minus that 999 minus 100. So that will be of 899. So then what it will do is it will increment that hundreds into 1. That 100 equal to 100 plus 1. 100 count will be incremented. Then it keep on repeating. Again check that binary in will be greater than or equal to 99. Yeah, 899 will be greater than that. So again it subtract again 100. So 100 will be incremented. So keep on doing this until it reaches 99. Once it reaches 99, it go for this, that 99 greater than or equal to 10. Yes, correct. So it keep on incrementing the 10's value up to 9 times. The 10 will be incremented. After that, the final value will be 9. That 9 will be passed to that ones. So with this logic, we will receive that 100 will be equal to 9, 10 will be equal to 9, and 1 will be equal to 9. So 999 will be received. That value will be passed to BCD 0, 1 and 2. That is the logic that will be passed in the 1, 0 state. Quickly do the logic. Clock. Begin. Then we have that case statement. Case state is when it is 0, 0. Then we have this logic that we keep all that initial value binary in. Then we can assign b in equals binary. That input will be assigned to that b in signal. Then we have that ones will be assigned with 4-bit zeros. Then we have a tens, hundreds. Next, we move on to the next state when it is 0, 1. Another logic we have missed is that we have to declare that the clock, rising edge of the clock, then we have to make that state as a state equals state plus 1. That we have to increment. Whenever you use that plus symbol, we have to declare the library, use IEEE standard underscore logic underscore unsigned .org. So once this is done, that plus, won't display any error. Then here when it reaches that 0 1 condition, we have that checking if binary in is of that greater than 100, that logic we have to apply. Binary greater than equal to 100. Then so it is at 100. Then we have that binary in equals binary in minus that 100. Then we increment hundreds counter. Hundreds equals hundreds plus 1. Then we have to keep the state to that 0 1 plus 0 1. Okay. Next, else if. When binary in is greater than or equal to 10. So previously we checked for 100, now we check for 10. That is 1010. Then we have to make that binary to binary minus that 1010. Terminate. So we can keep something like 8 bits of that value. 0000. Okay, fine. Then we can assign that tens value with tens plus 1. Again increment that keep the state to 0 until that last operation, that one's value will be assigned. Then we have that else part. Else we have that ones will be assigned with binary in of 3 down to 0. Because this will be less than 9, less than or equal to 9. So we can end this statement, and we have that another statement that when 10, then we have a logic that we have to assign that BCD 0 with ones, BCD 1 with tens, and BCD 2 with hundreds. Yeah. Finally, we have to keep that others. When others what we can do, we can make that state to 00. Then in case end if and the end process. So that is the logic we have created. So we have that initially we have a state with an increment whenever that when state is 0 0, it check for it assign that binary to be in. Then once tens and hundreds will be assigned zeros. Next, when that state goes to 0 1, then it check for the logic that B in is greater than or equal to 100. Then it will subtract and increment the 100 count until it is less than 100. Same way, it check for less than or equal to 10. It keep on incrementing the tens counter until that position. Once it reaches less than 10, it goes for ones and assign that input of 3 down to 0 to ones. So finally, that state will be passed on to 1 0. Here, it simply assign that ones and tens and 100 to BCD 0 1 2. Others will simply keep that state to initial state 0 0. So that is the logic. So next we can create a constraint. Create. So binary to BCD flash. This is for printing 10. Open the constraints. I'll copy that constraints clock and switch. Instead of binary in, we can assign that switches. Then we have to assign that BCD outputs. BCD output can be assigned to LEDs. We can assign that 12 LEDs and can rename them. Okay, LEDs were renamed to BCD 0, 1 and 2. Save it and generate bit stream. In the meantime, we can check the RTL analysis, the RTL schematics. So here is the RTL schematics. So there are so many conditions, so it looks lot of registers and adders you can see in comparators in the logic. Then we have a mux. So mux registers, adders, comparators, subtractor, comparators, adders and registers. So these are all the main things that that was constructed. So next we can turn on the kit and start programming. So bit stream got generated, open hardware, auto detect, and program. So there is some mistakes are there, I think. Let's view the code. Yeah, I find a mistake. It should be greater than or equal to 100. It check for greater than or equal to 100, but here we declare it as a less than or equal to. That is the mistake. Quickly save and regenerate the bit stream. Okay, let's program the new code. Now we can check that one. If I make this thing 1, then it displays something like 1010. So best way to find is, so 1001 is the 9 that is displaying 1001. If I make it as 10, it will toggle that next 5th bit high and display the remaining things 0. 1 for 1010 it display 10000. So that is the BCD output. If I make all the switches high, that 8 switches high, then you can see the output 255 it will display. So this is the 2, that is 0010. Then we have 5, 01015, and then last year we also have 0101, that is the 255. For 8 bit of binary input, we have converted to 12 bits of BCD output. Thank you.